running everywhere. Let me know. Let me know how the stream is over wherever you are. All right, YouTube is up. Come on, Twitch, you can do it. Twitch is up. And YouTube is noisy. Of course it is. All right. Not anymore. What about the chat? Are we in the chat? Let's try it. Welcome to Code Hangout number 68. And it looks like chat went through. Sweet. There we go. All right. Hi, everybody. Today, I'm gonna dip my toes into some solver logic. I don't want to build a solver. I definitely don't have the interest. And there's a fly. Of course there's a fly. Why wouldn't there be a fly? But for the feature I want to build, I feel that I kind of need it to do what I want to do. And basically what I want to do is I want to create a very simple but functional... All right, I'm going to have to do something about this fly. Seriously? You're going to sit in front of me right now? God. Settle down. Where was I? Yes, I want to have a quick tool to add up a few numbers on screen, but in a way that makes sense. And unfortunately, the primitive method of adding up the minimums and the maximums won't make sense to a human, because a human knows the actual rules of the puzzle, while my tool doesn't necessarily know the full extent of the rules of the puzzle. Yes, most of the time they're basic Sudoku rules, 1 through 9, 9 by 9, etc., but not necessarily, right? And it'll screw up badly on puzzles, let's say a 0 through 8 puzzle, or a puzzle with missing digits, or a puzzle with gaps or whatever. So I would like to try to do something that's in line with the existing tools. So I was thinking, okay, we already have a tool that has awareness of cells seeing each other to some extent. So it would make sense that this tool hooks into that the same mechanic, right? And that means that if that particular mechanism is flawed, then we can fix that mechanism and it'll fix it for everything, right? And the expectation of what works how is kind of maintained. So that's kind of what I'm trying to go for. So I've had a couple of different approaches, including the primitive ones, and I didn't like where they were going. So I'm going to select a few cells here as my test case, right? And in a situation like this, I'm going to do this. So this is now in the replay. So when I refresh the browser, these cells will be selected. But basically, we have a couple of regions here, right? We have this 10 cage, we have this 6 cage, which is filled incorrectly. We have additional cells, but these cells don't see this cell. But this cell sees all of them, right? So now I want to figure out what is, just using the algorithm of which cell sees which cell, what is the best we can do in terms of the known minimums and maximums and possible ranges of these cells, right? And I've done a whole bunch of code that does all sorts of little things, but it's all trying to take shortcuts, and because of that, it ended up being much bigger than it needs to be, right? So my goal right now is, so I have an algorithm that basically, try to subdivide its cells into groups, but I assume that they're mutually seen. So every cell this cell sees can also see the cell, which is technically correct, but those cells don't necessarily see each other, right? So this cell can see all of them, but let's say the 8 doesn't see the 1, right? So I'm going to try to change this now into an algorithm where I just have one-way links. So I just say, okay, for every cell, I just check what other cells that cell sees, right? And then I will use that information. I have a whole bunch of functions, and at the end, I'm going to remove most of them, basically, right? But find scene groups was the thing that was generating the groups. So I have so many bits of code that are all commented out, etc., and it's a bit of a mess. So I'm just gonna comment them out again. And yeah, here I was trying to do this. Okay, none of that really worked out properly. I'm gonna get rid of that. All right. And we're starting with these cells. These are our sum cells, right? So now what I'm going to do is I'm going to I'm not going to break down things down into functions first. I'm just going to do it one step at a time, right? So I'm going to create a data structure for every cell where I collect certain bits of information. So for each cell, I'm going to have a list of other cells that that cell sees from within our group only, right? I'm going to have some information about it, minimums, maximums, etc. The potential candidates I'm going to work out. And then I'm going to kind of loop through them and say, okay, the minimum value is, let's pick one and let's fill in the smallest candidate we can, Now, I don't know if that's always going to be guaranteed the minimum. So sometimes, let's say if you can fill a 1 and 1, and then the other one suddenly is limited to a 4, you'd be better off putting a 2 and a 3 in it or something, right? So I'm not even sure yet. I might have to call into the algorithm that calculates the, the combinations, right? Treat it like a killer cage, find all the possible combinations, right? But the problem with a killer cage is that in a killer cage, all cells see each other. While in this situation, that's not necessarily the case. So I might actually have to do a depth first search. So try all possible combinations and then just find this, And in the end, all of this to kind of find the minimum configuration and the maximum configuration to calculate the proper true range of what these cells could possibly be, right? So that's kind of my goal now. And if I can build that and it works, then that could potentially be a basis for future stuff, right? So, it's a little bit more work probably than it's worth. But it's something that I've probably should have done a long time ago, kind of structure the data more and kind of be more aware of what the data is, right? So first what we're going to do is we're going to turn the cell, each of the cell into a little data structure, right? So we're going to say something like, I'm using groups and cells and blah, 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 right? But I need to differentiate them somehow, right? So if we have the sum cells, I'm just going to call it cell info, right? And for each cell in our selection, we're going to create like a little bit of data here, right? And then after, we're going to output that data for all the cells. Okay, so, and I'm just going to return a little object here, and that object is going to have the original cell in it and some other things, right? So, one basic bit of information is going to be the value, right? So we have this little algorithm. So we have what I call the fixed value. So if the cell has a known given or what's called normal is basically just an entered digit. And to keep things a little sane, I'm going to only look at things that are integers. And I probably should translate this to things that are positive integers, because recently there was something with negatives. And with negatives, I don't think the system will work reliably. And it's likely that there's some special rule in place that the system doesn't understand anyway. So whatever I would try to do probably would break, right? So I probably should do that. And since there's a whole bunch of little checks here, I'm actually going to wrap that into a little function. I said I wouldn't write functions, but this thing is something that's been bugging me for a while. So I'm just going to do something like get cell fixed. And we'll start with a cell. And we'll basically do this stuff in here. So we'll do that. And then if is int val. So if the value is an integer, right, we'll turn it to an integer. And now if val is greater or equal to 0, return val. And if it's negative, we're going to return undefined. This just means we cannot reliably say what the value is in this cell. And we'll do something similar for the candidates, right? So here we're going to do let fixed equals get cell fixed. And then we don't have to do this other stuff, right? Wait, if I refresh now, I think the selection should still be there, yeah. So you see most of them will be undefined, but we have the 1, the 8, and the 2. And I'm going to do something like cell.toRC, just so we know what cell we're talking about here. And most of the time, we're going to be looking down here at the console output. So here are the cells, and we have the fixed values. So the next step is to get the candidates. And the candidates, you can treat the fixed value as a potential candidate, and you can treat an empty cell as a candidates 1 through 9, right? So probably what I'll do is I'll wrap the fixed cell stuff into the candidate stuff, kind of thing, right? So get cell candidates. Or maybe I should use a different word because it's a bit confusing. Options. Let's call it get cell options. Right. So we're going to basically get the fixed value first. And then if fixed is not equal undefined, then we're done. We're returning an array that contains the number, the value fixed, right? And we can probably do get cell options, cell here, and we probably don't even need to do this in here. So now these are just an array, and that means, okay, this is the last option for that cell. Now, if that's not the case, we got to look at the candidate properties. I'm not going to look at the corner marks for this tool, because the corner marks are more complex. So now we're looking at the properties, right? We're making sure all those properties are integers. And we're going to do and we'll kind of do this. Or we'll actually, shall we change isInt or create an isInt with isInt pause. And parse integrator equal to 0. That just, it'll make things a little more compact further down. So then we can, first of all, can do this, isInt pause, then we don't need to do this at all. And we just return this directly. We don't have to worry about negative values. Right. And then here we can just filter by positive integers. All right. Now we're going to look at our options, which currently should be string values, right? So there's only this one, the 1, 2, 3. And then here we can do map. And we'll just parse it. So that's an array of 1, 2, 3. And basically that's it already, I think. So we can basically just return this here. Boom. Right. And then finally, we're going to return an array with all the possibilities. And at this stage, I'm just going to simplify it and assume 1 through 9. For other cases, if it's possible at all, I'll have to revisit how I'm going to figure that out. Hey, Chaya. Chaya. Yeah, it's been a bit off and on. Although I have streamed last weekend, but it was quite short. So I've been working on this for a couple of days now, and I'm not happy with where it was going. So I'm going to kind of start over and see if I can do the proper thing and see if that gets us somewhere. Okay, so now we have the options, right? So we have the cell. We're going to return the options. And that's our cell options here. And if we output those, it's basically this stuff here. So the cell and the options. And the options are empty. Why would they be empty? Turn. Oh, yeah, no, yeah. Because this will filter and map, and we have no filter for the empty array. So let options equal this, and then if options.length is greater than 0, return options. And that should give us the 1 through 9 for the other cells, basically. Yeah. And we still have the cell references and all that stuff. All right. So next step is to get a list of cells that are seen by the cell, so we can basically, as we are modifying each cell, we go to all the other cells that the cell sees and basically say, oh, okay, if this cell is a 1, then any cell this cell sees cannot be a 1 anymore. And then kind of recursively do this until we have the least number of options available. All right, so seen cells, we calculated using, well, whatever I was doing in here, right? No, not calc cell group. It was the scenes, find scene groups, right? So I think it was this, basically. So basically we're finding all the cells the cell sees, which is obviously a bunch, and then we filter it by cells that are within the sum of cells region. And instead of seen cells, we're just going to call it seen. And actually, we're just going to stick it right in there. I think that should be it. And instead of spreading it out like this, I think it might be easier to pop it open. And then we can look in. And then, so for example, this cell sees 3 other cells. This one sees 3. So this is our magic 1 here in the middle, which sees all 7. So whatever, let's say if we're putting a 1 in here, this has to become a 1, right? And it'll also tell us when we have to backtrack. So if we're eliminating all options in this, well, we have to be careful, right? Because it's very possible that there's no options for a cell. So I'm not sure if we should mark that as a conflict. It's obviously a conflict, but that's not really the point of this tool, right? The question is, do we, in the display, which is up here, do we mark this as an invalid situation, right? All right, so this is now our initial state. And basically what I'm imagining to do now is kind of saying, okay, which one, like we're filling in an option here, and how does that affect all the others, right? And the question is there a better way of doing that? Is it, should we, like, if we're looking for the minimum, should we fill in the smallest value first, or should we fill in a random value and then go through all the options, et cetera, right? Excuse me. Because we're kind of like, a little bit, we're doing playing a little bit of a game of what if, kind of like a chess algorithm, we're like looking ahead and saying, okay, if we were to fill this in, where would we go? But instead of trying to solve the puzzle, we're simply trying to figure out what is the biggest and smallest value we can put into this set of cells, given the current state of the board, right? Now that I said current state of the board, it occurs to me that this doesn't take into consideration the rest of the board. So, but we kind of do want to do that, right? We don't want to put a 7 in here. The cell under the 8, for example, because it sees a 7. So we probably don't want to exclude the cells that are seen by the others, which we did with this filter. So probably what we need to do is we need to have both the seen cells, and then we have to, what's the reverse of seen? The watched cells, right? So the filtered cells as well, because if we're changing a cell, we want to update the watched cells, right? I'm just trying to think if that's necessary, right? Or if we just keep always looking at all the seen cells as we're modifying each cell, if that's good enough. We're basically just solving for these 5 cells or whatever that's under our current consideration. My nose is starting to itch and I don't know why. It was fine until... Excuse me, it was fine until I started the stream. Alright, let me know if there's anything off or on with the audio, you know, the usual stuff, just to make sure I don't lose any chat messages. I should really have a button for that. Well, besides this one. Alright. So, watched cells. So watched cells are the cells I can affect, and seen cells are the cells that I need to consider. What I just did, I'm gonna undo again, and it's gonna happen a couple of times. I should probably learn from it and not just keep removing that kind of structure. So we're gonna do this for the seen cells, and then watched is the seen cells minus, well, limited to the actual area of cells that we're looking at. So if we're doing this, and I look at, yeah, so this one watches 3 cells, but it sees 21, right? So this cell probably sees the 7, etc. Awesome. So now we need a couple of helper functions. So for one is to clean up the current state of the cell, right? Because the cell has options in it that it shouldn't have, that aren't possible, according to its seen cells, right? So let's do that one first. And I'm gonna just put that as a function over here quickly. So update cell info. And I think I'm gonna do a function that does it for one, and then I'll have the loop of doing it for all of them elsewhere. And probably what we want to do is keep track, like if update cell info. Yeah, no, it makes sense, right? So I'm updating a specific cell, and now every other cell that is watched by that cell, and watched is the wrong word because it's exactly the reverse, right? Maybe observed. I mean, affected is the actual correct word. Or linked, maybe. Excuse me. I don't know why my nose is always doing this when I start to stream. Yeah, let's change that word. It's bugging me. Affect. Let's do that. All right. So update cell info. And we're basically just passing in one cell info block. So cell info, yada, 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 yada. So just so we know, this is all happening. And then we'll do something like this. And just see what happens. Well, nothing will happen. It'll log this line out. Okay. And cell info 0 will be undefined. No. The result will be undefined. But this is actually cell info for... And this fly is... I haven't had a fly in here for weeks now. And I don't know where it came from. Anyway. It's quite hot, so I'm a bit sweaty. So the fly is probably quite intrigued. All right, so what we need to do is we're looping through all the scene cells. And I don't know if scene cells include our cells. If they do, we probably want to remove them. So cell info dot scene dot index of cell info dot cell. So I just want to check if the scene cells list includes our cells. If it does, we'll probably just remove it. 8. Yeah, so it does include our cells. So we probably want to avoid that. So let's change that. So scene. We probably want to filter, scene cell is not equal to cell. And we probably can do that up here, since we don't want to include that in the other one either. And to make it short, I'm just going to do this. And now it should have a -1 here for the index. Okay. So now we're going to loop through the scene cells. Like that. And what we're going to do is we're going to get the value of the cell. I'm just going to call it fixed, just to stick with the terminology. All right. And then if it's undefined, we'll just move on. Nothing to do here, nothing to see. Otherwise, we're going to look at the options. And I'm just going to output this information quickly, just to get my head around what's going on here. Right. So 1 is present at position 0, 7 is present at position 7, for example, in this case. So what we want to do is we just want to remove those, right? And the removal is done like this. And it bugs me that this is a multi-line thing, so I'm going to make a helper function. If it's not -1, options.splice idx1. So that should be enough. And it deals with the option not being present. So we're just going to say remove option, options, and fixed. Boom. And here we're just going to do we're just going to output options before and after to see how they have changed during this operation. And I think that's all we need to do. So for example, we removed the 1. So we're looking at the first cell here, 2, 3, 4, 5, 6. We removed the 7, 8, 9. Yeah, so we removed the 1 and the 7. Exactly. So this one, now we've removed the 1 and 7. Now, because we know the sum of the cage, etc., there might be more to look into later on. But let's proceed with this for now. Now, if we do this for every one, we only have sort of the first order, right? So we don't know what happens if we actually fill in a value. So we don't need all these. Oops, we don't need all these anymore. So what we can do now is let's say info for each, and we basically can just do this. And that should clean them up somewhat. Oop. Update cell info. Nope. Now I have to be careful because here I'm calling cell info the group, and here I'm calling it the individual thing. So I have to be a bit careful. Maybe if I do it like this, options, scene. So we're looking at scene, and we're looking at options, and I don't think we need anything else here. Okay. So now we have the 7 options on the first cell. On this one, the option is just 1. That's correct. Now the options for here are excluding the 8, the 1, and the 2, because it sees all of these, right? Now this one used to be 1, 2, 3, but we removed the 2. Okay, sweet. That's the 8. This one is only 1, 3, 4, 5, 6, and 9, because it sees a 7 here. It sees the 2 here. 3, 4, 5, 6. And it sees the 8 here. Excellent. And then this one is only a 2. Okay, so far so good. So this cleans up all the cells as to what values they currently see. So now the idea would be to have a recursive algorithm. So the easiest thing would be to just go through all the options, right? To pretend, hey, what if I filled in this option in this cell? What's the overall sum, right? And considering that we're dealing with a limited number of cells rather than solving for the whole, we could go ahead with that. It might be a little bit tricky if we're solving for the whole, right? Then we're just, like, if somebody selects for the whole thing, then we're basically just, then we're just building a solver, right? A very primitive one. So the other question, or the other thought I have is, can I solve for minimum and maximum simultaneously, right? So can I say, hey, what if we put the maximum value and what if we put the minimum value in here? The problem is minimum and maximum overall value is not necessarily achieved by min-maxing in any individual cell, right? So sometimes one cell needs to be lower to enable other cells to be higher, etc., especially when cage constraints come into consideration. So I'm not sure if I should just do like a primitive depth first search solver at this stage. I mean, the other thing is we're not actually solving, right? Because we're happy to end up with a state where we can't push any further. Except, no, not really. Actually, we're building a solver in a way. Now I'm realizing what I'm really asking for is a solver that finds all possible solutions and then sums up the smallest and the largest. And I don't know if that's something I can do. Like, for a limited number of cells, I can, but if you have a maximum number of cells, you know. I mean, the alternative is, if I pull out the cages, I can obviously find the minimum value for the cages. For the cage, it's much easier. And then watch individual, well, no, not really, huh? Because I can't just take the minimum value of the cage, because because which numbers you put in the cage can affect what other numbers you can put elsewhere, right? So that's also kind of important. So I guess one helper function that I would want now is to say, okay, fill in one value and then update. So, so let's wrap this into a function. Const get cell info cells, and it's basically just this bitty, right? So we're just going to do this one. That should still work. Okay, so const what do I want to call it? Try value. So there's another consideration, right? We need to know when we're finished, right? And we're basically finished when all cells are filled, I guess. So it is a solver, isn't it? I did not want to actually, you know, the title literally says not a solver. I didn't want to build a solver, but I'm feeling that that's basically what I need to do to make it work the way I want. One thing that's bugging me right now is that if a value is filled in badly, I cannot, like, I don't know if I can use the killer cage. Right now I'm using it for a vision check, but not necessarily the sum of the killer cage, right? So that might be another constraint I'm adding, but then that's really just a solver thing. All right. I'm also struggling to see, like, what affects the quality and the speed of the solving mechanism is the choice of which value to fill in. And right now, I really don't have any, like, again, I don't want to build a solver, so I don't really want to think about that. I don't actually want to have a strategy. I just want to, you know, I could just do the first one, right? So, let me think. Okay, so first of all, I need to output these in a better way. So what I'm gonna do is I'm gonna do something like this: map, and I'm gonna map them to the RC value of the cell and the options. Something like that. I don't know if that'll render properly. Yeah, I think I need to do a for each loop to do these. Well, name info.cell.2rc info.options cell info.map. Wait, is this allowed? Oh, straight const. Here we go. Excuse me. Yeah, this won't render nicely. Let's do it differently. If I do this, yeah. So now we can track as we're updating what happens, right? And we can manually step through it right now. So I'm guessing to solve fastest, we want to take, because we're not looking for an accurate solution, right? We're just looking for the minimum maximum value, right? So to reduce the options the fastest, we kind of want to sort them by the value with the largest number of candidates, right? So if we do something like consort by most options, and we have an A, B, and we'll do A dot options dot length minus B dot options dot length, right? And then if we do something like this, so then it's sorted like that. All right. And we probably, yeah, we probably want to reverse this. We want the most options first. Whoops, sorry. All right. So now if we take one of these candidates with the most options, and I'm trying to remember if the sort permanently modifies the array. Yes, it does. Which is fine, I think. So probably what I should do is split these out. All right. So now we can just go into the first one. 0 options dot length equals 1. And that will basically change the options to the first value, which should be the lowest. The options should be in order. And I'm just going to put that there. So the logs make a little bit more sense. Yeah. So now we've reduced this to a 2. And we can update it again. So we'll do this before we show it. So now this 2 should have affected some of the others. Well, actually, it didn't affect the others because the others already had their 2 removed. Well, it didn't do much. All right, fair enough. So if we do, and now if we sort it again, so that'll sort it again, and we do the whole thing again, right? So now this one became, so 704 became a 3, and that 3 removed, not much actually. It removed the 4, 5, 6, and 9. Ah, no, it removed 7, 5, 7, 4. Yeah, okay, 7, 4. So it didn't actually remove any of the others. Excuse me. So 7, 4, and I think they're off by 1, so this would be 8, 5. So that would be no, 7, 4. 8, 5 is the 8. All right, 7, 7, 4 then. So this one, being a 3, didn't remove the 3 from 9, 5. Why not? 9, 5. So I feel my update cell info didn't work properly. So, if there's an update, let's output it. And let's see if that tells us when this option got removed. So, none of these options are getting removed. Okay. So it's not doing what I thought it would be doing. Ah, I'm an idiot. Right. It's looking at the existing cells. It's not looking at our modified values because we're not actually updating the cells directly. Okay. So get cell fixed actually needs to take into consideration the cell info as well. So let's do a get cell val here. Pass in the cell. Right. And this needs to be dependent on cell info for now. All right, so get cell val basically is going to be, and we're going to have to index that back in there. So let cell info equals, let info equal dot find cell as C equals cell. If info undefined, return get cell fixed. Now the value of the cell we want to do the other way around, right? So if info is not equal to undefined and info.options.length equals 1, then return info.options 0. We're going to return what's in the options. Else we return the cell fixed value. And we're going to use that in the update call. So that should do the trick. So now we've removed a few additional ones. And I think if I do this, well, we might gain a bit of extra space here. Right. So first round, this is our status. Then we're replacing R6C3 with a 2, which comes down here. And it doesn't cause any additional removals because that's this one, and it isn't seen by any other cell except for this one. So in fact, wait, row 6, column 2. Row 6, no, column 3, sorry, yeah, it's this one. It's not seen. Shouldn't that remove a 2 from this one? It should remove a 2. Ah, but this one already sees a 2, so okay, so it doesn't make any other change. All right, fair enough. So the next step is we're removing, or we're setting this one, RC723, and that causes the 3 to be removed from this guy, which is R, so this doesn't have a 3 anymore. All right, and now we're almost at a solution, right? So this algorithm-ish thing so far seems to do a thing, right? It does a thing. I don't know if it does the right thing yet. All right. And if we do it one more time. All right. If we do it one more time here. So this is now a potential way of filling it in. Let's try it out. Let's see what that would look like. So this is row 7, column 4 is a 3. Row 7, column is a 3. Row 7, column 5 is a 1. Row 6, column 3 is a 2. Row 6, column 4 is a 1. Okay. Row 8, column 5 is an 8. Row 9, column 6 is a 2, and row 9, column 5. Why is it empty now? Okay, so this means there's no solution, right? So this one is one we should abandon. Okay, so then the question becomes the backtracking and all that stuff. So to backtrack, you obviously need to have access to the original information. So now if you're recursing, that information would be stored in your environment, but that gets expensive quickly. Now we can potentially implement this here because again, we're looking for relatively small subsets. But of course, if I do a control A, it's basically just doing a full solve or, a few steps of a full solve. So I have to be a little wary here. I have to think about how I'm going to do that. But first of all, I want to go back to our original selection. If I refresh from here, we're back to here. Okay, and I got to figure out how I'm going to actually do this. So let's write this out in steps or points. Identify, and remember, we're looking for min and max values, right? So best min candidate. So the primitive version is to just use whatever, the lowest or the highest value. Now the second thing is we need to roll back, right? So if the smallest didn't work out, we need to now try the second smallest, right? So we need to actually kind of loop through them at any particular point. And identify failure states. Now the other question is, what shall we do if there is no valid way of filling in the cells? I mean, worst case scenario, we just put a question mark in there, right? All right, so this is basically a step. And this is always the same, so we can literally just repeat this one, as long as we detect our exit clause, right? Now, we basically want to loop one through the next, right? So in a recursive algorithm, the first thing you want to do is you want to have your exit clause, right? So I'm going to do a very simple one where I just step 5 steps for now. So we're going to create a function and find min max. Right. And then we'll do that steps equals 4. And then here we do step. This is our recursive inner call. And here our exit clause is if steps equals or equals 0, turn. Steps minus minus. And now we're basically gonna do one of these. Now one step yeah, so it helps that we're always going to look at the first cell. So we need to, okay, so we need to know which candidate we're currently looking at as a sort of global state. Except no, it cannot be global, it needs to be local. Okay. So to start, we want to update and sort. So that's our starting step here. And we're not going to do any of these anymore. Right. And then we want to do a step. And one step is basically resolving this particular cell. But of course, we also need to recurse. So it's going to be a bit tricky. And what do we do if... I was going to say, if the last cell we looked at is not the smallest now, and also by changing the order, is it guaranteed to... It should be guaranteed to be back in the same order once we've restored things to how they were. So this is a little tricky, and I might misstep here. I haven't done this kind of algorithm in a while. So let's think. Again, we're recursing. So if we're less than steps, we're returning, okay. But the other clause is our first options length 1? Right. So if... And here we're going to put a little console.warn, max steps reached. Here's 1. We'll do something similar. Console.warn, first item has no options. Okay. Now we want to loop through the options, right? So let I... 0. In fact, we can probably just loop here, right? For let I equals 0, I smaller than. And we probably want to do a local copy of the options. The thing is, the sort. That car was info 0. So we want to make sure we're always looking at the same thing, right? Less than car.options.length I++. Options I. So if I do this, where do we end up? Some cells, let's get rid of that. It's really helpful right now. It's kind of spammy. Why is it outputting twice? It's outputting once before and once after. Actually, the after, I don't see that. It's not down here. I don't think that's used. What I missed. Cell info. Cell info. Cell info. Sort by most options. We have this one. Where's the second one? Oh, because the whole thing gets called twice. All right. confusing myself here. Let me just check the other chats. Everything's quiet on the Twitch front. So this does not look sorted. This does not look sorted. Because we haven't called step yet. Called step from inside here, but we haven't called find min max. All right. So let's do this here. Actually, let's bring that down here as well. Hey guys. All right. Cannot reprogram. Okay, so now we're actually finally calling into this function, which we weren't doing at all before. 289. Oh, because we're not passing sound train. And we can probably move this into here as well. Right. So, in fact, the get cell val could go in here. Options is not defined on line 285. Yeah, current options. Okay, here we go. So this is before the sorting, etc. So let's do this after the sorting. Before the step, and then we'll do the same thing after the step. So before the step, it's sorted. Now we're looking at the options of the first item. 6 options. 7 with the 0, right? All right. Except right now we're not doing anything with the options. So the idea now is we're basically gonna set current options to the option. All right. So we wanna back the options up as well. So if we're recursing out again, we can, you know, undo this whole thing. So now the idea is, and obviously the step counter is going to mess with this, so we're going to be a bit careful here. But basically what we're going to do is we're going to set car options.options equals options I in an array. And then we're just going to call step again. Except step needs to do all of this. So this is actually going to go inside step here. And what does this look like? Other than a total mess. So the first time we're outputting it, it's here. Then we're looking at the first options value. First item has no options. That seems unlikely. Cell info. First item has no options. Ah, wait. First item. Oh, okay, so this has to happen after the update and the sort. Like that. Like that. Something like that. And I feel like I want to output this inside the step function. So after all the sorting, we're going to output this. We're just going to do something like steps. Right. So we're going to warn this so my eye can kind of follow along where we're at. So we're starting from step 4 and we're working our way down, right? So we have clear summary, step 3. So it looks like this. That the first one gets set to a 2. Then it looks like that. And then we do the same thing with this one being set to a 3, and then comes down to this one. And then says first item has no options. And now it should back out, except we are out of steps. So we need more steps. And I think we need a sample, a smaller sample. So let's try just with these two. Yeah. I'm just gonna wait for the persistent storage. And it didn't do anything. Oh, because it's a cage. Yeah. All right, let's exclude cages for now. So let's do these two. It's inside a cage. All right. Let's do these 3 cells. No, 3 cells should be fine. Better than the other ones. All right. So let's see. So now we have a 2 there. For the central one, we have a bunch of options. And for the first one, we should have 2. Except we don't have 2 because it's excluded. So let's change this to a 3. 3 and a 4. I'll select these 3, color them, so selection gets maintained. All right. Now it makes more sense. Yeah, we have these options for the central, 3 and 4 here, and the 2. Okay, so the first thing is we're removing this. We're setting it to a 1. And we're here. We're setting this to a 3. We're here. First item has no options. Now we're backing out. So now it hits cell info. Why does it hit cell info after first item head? Because this return should hit us back into this loop. Final max, step 8, 9, 8, 7, first item has no options. So we're breaking out of this recursion, but this is, we should be two levels deep at this stage, right? So this step call, we're coming back to here, and we should hit the second loop around this thing. Why are we not doing that? Something isn't working the way I think it should. So we have options, after options. First item has no options, 3. After options. Okay, well, we're not resetting it here, right? So that's kind of... So options, car.options, options, car.options. After options. 1, 3, 4, 5, 6, 9. The problem is, at this point, car has changed, right? So car.cell.2rc. Well, current, should have changed, right? Despite the sorting. In fact, the sorting needs to happen in here then, because we need to undo the sorting, basically. Well, not the sorting itself. Trying to think. The update? Yeah, the problem is the update cell info updates all the other cells, so we have to undo all those changes. And I don't want to track everything I'm changing. So what's the easiest thing to do here? Serialize the whole state? I don't like that either. I mean, we could serialize the state. I mean, it might be okay right now for development, but ultimately we don't want to have to do that. It must be, there's a better way of doing this, but the more I think about it, the more I'm going into real solver territory, and I'm trying to avoid that. Other people have built solvers already. They don't need me to do it. I actually have a solver, right? So if I have a solver, I mean, this is a little optimized, right? How do I back out of stuff? Because this is not a recursive algorithm. So find next solution. Has broken cells, return false. Does it just... It just, like this just backs the whole thing up and then restores it, the whole thing. Okay. So if I simplify the state and serialize it, that's what I was doing here. And I was using the puzzle 729 format, which basically just is a single array of all the options per cell. That's why I did it like that. And it doesn't have all those other references and all the other stuff. I mean, that would be one way of doing it. And one optimization would be to have it per map to the cells themselves, right? But at least it would be just one array that we need to save and restore. Is it? But is this recursive? No, it is recursive because it calls itself, right? Yeah, this is inside here. So that's exactly what we're doing there. Oh, I was hoping to clean this up today quickly. But I'm really going into solver territory here. It's the restoring of the state after we backtrack that I need to solve. And the only state that we're changing are the options. So if we change the options to be stored in a different shape, because the problem is right now this is a complex object, so we can't save it easily and quickly. And by resorting it and by changing the order, let me think. How do we choose which value we're gonna set? I think we're not choosing at all. I think the whole point to make this fast is we're just going in order and we're just trying them all. So if I don't choose a particular one and go in order, then I can get rid of the sorting, which is relatively expensive, and I can save the options in a bigger structure. So right now the cell info has this. So basically the idea would be to flatten all these out, right? So to have separate arrays. So if we're doing this, let's isolate this in here. Get rid of this. So we keep those algorithms. This we're now just gonna pass in cells like that. We're gonna temporarily get rid of all of this, right? And what we're gonna do is we're gonna kind of replicate this a little bit. And this, there isn't much happening here. And we're going to do this up here. Keep things simple. So what do we need? We need a singular options array that indexes into the whole thing. And I think there was helper functions here to find out if a particular thing has all its options exhausted already. I think it was kind of this thing, if you want, minus minus. So we're basically finding the first digit that's not a thing. If cells greater or equal to 81, partial to 81. If puzzle has broken cells. Yeah, so there's a little bit of looping happening now because we can just look at the length of the array, but we're saving on all the splices. So the idea is basically instead of having variable length arrays, we have a singular array that basically looks like this, right? So this would be 4 cells, but if the first cell is a 1, it would actually look like this. And if the second cell doesn't have a 1, it'll be like this. And if the last cell is a 4, it would have 3 dots, a 4, and then 5 more dots, right? And this would be our array. And I think I'm treating it as an actual array of values here. So let options. And then we still want the affected and seen arrays, but now we're just bringing them up one level, right? Cells we already have. And we're just gonna do this. Like this. And then we're gonna go through this like that. And then we're going to do, and then get cell options. Obviously it doesn't make sense to do this. We're gonna bring this in to in-house. Right? And in this case, yeah, we want to just use get cell fixed. If fixed is not equal to undefined, we're basically going to go this is it's like a simple thing, but it's noisy code. You know what? No, we're gonna do this, right? So let cell options equals this. Let's do this. And then let's say console.log. We're just gonna do that. Just to make sure it's doing something sensible. And then we're actually going to do for let I equals 0, I smaller than 9, I plus plus log IXI and cell options dot. Now I gotta translate values to indexes. And is shifted by 1, so off by 1 errors, abound. It's like I'm almost tempted to just if I start. I think actually yeah. I'm just gonna start with a static array and just something like 1, 1, 2, 9. Just gonna do this, right? And then we're gonna do something like this. 1 to 9 map n cell options dot includes n if it includes n, we're gonna return n, else we're gonna return a dot, for example, right? So now it converts a 3 and a 4 into an array like this, yada, 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 right? And we can probably just do this. And then we can just use Boolean, although this doesn't parse easily. Empty string. Yeah, that's fine. So then we want to add these into here. We actually want to, for each, and then we'll do a options idx times 9 plus yeah, and I plus I equals this, I think. And then at the end, we can look what options look like, and it should combine all the options for all the cells in order in an easily indexable way that we can then easily, yeah, so 3 cells will have 27. The first digit has 3 and 4. The second digit has 1 through 9, and the last digit has only 2. Okay, so options sorted, affected equals this, but we need to first calculate scene, and then we need to set scene. So scene idx equals idx, and affected is that, and I don't know what that even is there. And then we have options, we have scene, and we have affected, and it should be more performant, and it should be easier to kind of, you know, clone the state. And scene, scene, variable name overload. And this is just a cached version of that, so we have access to these other arrays. So we know all the cells seen by each of these 3 cells, and we know all the cells affected by these 3 cells. And now we should be able to go through this whole thing again, but now referencing these 3 global variables here. And yeah, like once you minimize it all down, it's not too terrible. All right, so now we're going back to running steps. And now we're gonna redo all of these without the sorting this time. So the update one is the tricky one now. So update. And now we're doing it by index, right? And I don't think we ever need to update a singular cell. So we're just going to call update cells. So here we're doing update cells. And then we'll just for our all of this can be optimized, obviously, and now it'll be much easier to optimize it as well. Right. But now for each cell, we also want to loop through the scene ones. And in the future, we can optimize it by obviously just updating cells that are actually getting modified. So the update would happen when we're actually doing the modification, rather than for all cells, right? in fact, the only reason I did this because I wanted to have an initial update for all cells, but we didn't need to do that every time. All right, so actually let's target the cell, right? So let's just do this IDX, update cell, and we'll just do the for loop here. Something like that. And then when we update the cells, we're going to do scene IDX, boom, for each cell, not fix get cell val. Now get cell val won't work outside of here anymore. So we're gonna make a copy of this, and later on these functions are just gonna all disappear. So we have update cell, we have get cell val. Now get cell val here. Yeah, so I was just trying to figure out how we're going to go from the cell back to the index into our thing, but it's actually very easy, right? So our cell IDX equals cells dot index of cell, right? And then we can do this. And this we don't actually do yet. And then steps, I'm just going to reduce it right now just in case something bad happens. Yeah, so now we have the same situation that if cell index is -1, if cell index is not equal to -1, and now this is the thing, right? So now we have the problem with identifying the actual strings, yada, yada, yada. Now, I don't remember how I did it here. I might have done something silly with strings and replace and all that. Basically, you know, to find if so we basically want to look at, well, we have cell index and options. And what's the cell index? Cell index options 1, 2, and 0. Right. So we gotta do a little loop here. Can I just reuse an existing one, please? Something like that. And we want to look at options. Options cell IDX times 9 plus I. And then we basically have to look at all of those and count how many of those are. So it's relatively clumsy, but the individual steps are actually really fast. So that count. If integer count plus equals options 1, 0. Boom. Does that get me to where I want to go? I think I have a mosquito bite in my head. Gee. Count 2, count 1. Yeah, so that's basically our equivalent of this. And if our count was, if we had a value and the count was 1, then we wanted to return that value. Except right now we're not actually saving that value. There was I had the same issue here to actually get the value of a cell. It's basically this thing, eh? So now it makes a lot more sense to have this in an if statement. If this count plus plus and val equals. So if, and I don't really care about this as getting assigned more than once. In fact, no, we need to. Yeah, we need to. Feels bad to resolve this twice, but I don't care right now. So count val. Right, so if count is 1, this should get us the value. So count is 2, it gets us the last value anyways, but you know, that doesn't matter. All right, all of this just to basically replace this one line. So if count equals 1, return val. And then finally, if neither of these is good, then we return the gets fixed value, and we're now down here where we're outputting this. And that should get us the current up-to-date value for that particular cell. Righty. So, return value, return this, fixed. Why are these all dodgy? What am I doing here? If fixed equals undefined, return. Ah, okay, yeah, because the board is empty, right? So they're all undefined. And you know, rid of that. Slowly. So now it's actually returning some values here. And then remove option is obviously a lot easier here. So and we're looking at options dot slice idx plus 9, right? So these are the guys we're looking at, and we want to remove number 8 from here, right? And the correct way of doing that is fixed -1 equals empty string. So now fixed. Let's add an 8 here. Just so it has something to remove, right? So that 8 should now get removed. And to see it getting removed, we probably want to show before and after. So we have a 3, 4, 8, and now the 8 gets removed. Boom. So we have the 3 and a 4. Are these... Ah, it's times 9. Times 9. Times 9. And times 9. Or is it just 9? Is it just a length? I don't remember. Ugh, I'm tempted to just use zeros or something. Yeah, shall we just use zeros? Where did we set up the original values? In here somewhere. That was the wrong. I just closed the whole thing. Let's hope that is not a setback. Doesn't seem like it. Thank God for OptSafe, right? All right, so that's the 3408, and then that's the 1 through 9 for the central one, and that's the one with just the 2 in it. Okay. And all my collapsy things here are just rubbish. Clear summary, is that where we're doing all this? Nope. Calc range, calc fixed, get cell, rem options, calc cell range. Okay, here we go. Oh, geez. Yeah. I'm gonna clean this up a little bit here. Find min max, get cell val, update cell. All right. So the updating of the cells is happening here. And then we can output the options here. And we should get that 8 removed, basically. That's basically all we're looking for right now. Yeah, so that removes the 8 that used to be here. Okay. So now what we've gained is that we can now easily save the whole state before we move on to the next thing, right? And let's clean up these. So that basically takes care of all of this. I'll do this. If I do that, does that make sense? So options, yes. These we can probably hide for now. I'm just trying to clear this up. Okay, well, that removed the 8. All right. And now, first item has no options. So we can probably do without that for now. By the way, doesn't look like I'm going to be able to finish it this stream. My apologies. Trust me, I'm more disappointed than you guys will be. So, basically now I'm kind of replicating this. It makes me kind of sad because, I mean, this code was never meant to be expandable. This was always meant to be very fast, quick, simple implementation of a basic 9x9 solver, right, for classic Sudokus. And this is kind of a different scope, but it's replicating some of the functionality. And I almost feel like maybe I should take the time to build a higher level infrastructure here, you know, like style classes and all this sort of thing. But I'd like to get a functional prototype ASAP and then take it from there, you know. But one thing we can do now is we can now easily serialize the whole options list and then go into it, right? And sort of step by step try out each option and see if that improves anything. We're still limited to 3 steps. So what we're doing here is, so now we don't have a sorted thing, right? So basically what we want to do is, same as here, we want to basically find the first cell that has, I think here, I'm literally finding the first option. But here I'm actually putting it into the, wait a second. Set val. If puzzle is not equals to dot 1 plus di. What I'm thinking right now is, wouldn't that also find cells that are filled in? But I guess it doesn't care because it then moves on to the next thing. So this works a little differently. So we have to, because basically what I'm saying is now we have to actually find a cell that has more than one option. which isn't clear or easy to see from this, which was easier to see from the other structure. So if we, let's use C for looping through the cells, right? And then O for looping through the options. I don't like this, that I have to count and then... That's one thing I don't like about this structure, that it's... I'm almost thinking is having another structure that caches the just the values so we can just look at the length of them. Is that going to be better? But it's an optimization that I don't... It's just annoying that I have this low-level thing now that I have to fiddle with all the time. And it's gonna slow me down. Yeah, I don't like it because now I have to count through all 9, and then, or I have to keep track of the count, and then I have to find one that has, you know, or maybe not. Maybe I just go like the solver, and I just go through the cells. Let me think. So maybe I just don't care. Maybe I'll just put that one in and then move on to the next one, right? So the DI here... Oh, I'm an idiot. This goes the other way around. It tries all the values. Ah, and which cell am I looking at is done elsewhere. And then we're looking at the next cell. Ah, okay. So this makes more sense, I suppose. So if I rename this to solve, and then we're solving for a specific cell index, right? So it steps through each cell and then... Okay, and then the update here should actually happen once on the outside. It doesn't happen in here, right? Max steps we can actually do without. Don't need that anymore. We can do a solve, and we can say what we're trying to solve on. Right. And now, we don't actually do this. We do that, and we're basically... I'm just gonna... And we only need to do a singular loop. Whoops. Sorry about that. Okay. Yeah, I'm relearning the things I had known in the past. So basically we're saying, okay, solve for the first cell implicitly. And the way to do it is to find the first candidate on the cell that's a possibility, right? Then we're setting that cell to that value. Now, we're basically ignoring the case where that cell only has one candidate. Because it doesn't matter, right? Nothing changes. Then we update the board state. And before we do this, we save the board state. And then we move on to the next cell, and we solve for that one, right? And we do that once for each cell. And then only once we've tried each cell, then we're backing off. And then we do the whole thing again. We go back to we restore, right? So we're doing a depth-first search. So the number of levels we're saving is how many cells there are. And the selection is relatively small. So we might, in this case, we're only storing 3 states, right? So I think, and instead of cells.length, obviously, this goes straight from 1 through 9. And then here we're saying that if options cell idx times 9 plus I is not equal to 0, right? And then basically the whole set val, you know, we're just filling it in. Now here we're using strings. But this should translate easy enough. Sorry, I'm trying to type and rub my belly at the same time. So, and let's just change this to IDX to make it more concise. So, yeah, So now we're looping through all 9 values, and we're setting them to if di equals I, that's also 0 through 9, then we're setting it to di plus 1, else to 0. And there's something here that's not right, and I gotta figure out this. Here we go. That's what's wrong. Right. And now after this, we should be able to output options again. So this is gonna spam out a bunch of stuff, right? And it actually don't do much, right? But you see, it replaced the 3 and 4 with just a 3. And it didn't even care about getting, well, do we have to get rid of the 8 here? I'm not even sure. But anyway, so now we've replaced this cell with a 3. And now we're basically moving on to the next cell. And we want to do the saved state before and after thing, right? So, saved puzzle. And here it's actually the reverse, right? But, yeah. And we do that inside the innermost loop. So we're doing that in here before we modify options. If options I is not, no, inside here, okay. So inside here, we'll do let saved equals options. Options. Then we'll do the set val, then we do the recursion, and then we do the restore. So that's the set val. And then the restore is just options equals saved. And then the recursion is solve step. Let's just do that. Solve step. IDX plus 1. And then we're restoring it afterwards. And then solve step is just acting on this one digit, right? And infinite loop. We have no exit clause. Yeah. There's only so many cells we have. If IDX is greater than cells.length, return console.warn all cells processed. Now, where does the... Ooh, yeah, everything crashed. All right. So let's refresh this. So what happens, right? Solve step. So it's doing a bunch of things here. All cells processed. Is this still infinite looping? Options, set timeout, solve step 4. All cells processed. Why is this doing this so many times? Also, how do we actually record the solutions? So the has broken cells thing is the first thing. The thing that I'm not doing right now. Solutions. If cell equals greater or equals 81. So that's a solution, right? So this all happens at the beginning. So at the beginning, we're checking if we have a solution. And this is basically if cell is greater than, greater or equal. All right, and then we're console.log. So, and then we're just going to output the options. All right. So yeah, so a solution is basically, each of these would be a solution where we basically only have one option per thing, right? And if we do it like this, it won't look as messy. So these are all the potential values. Now, I'm not doing any cleanup here. So yeah, so we get double values here, right? So now the job is to clean things up in between. And here I'm going to do console.log try. I'm going to say what were we trying, right? We're trying for cell IDX value I. All right, so we have tries here. So we're starting with these options and we're trying for cell 0, we're going to try value, well, I, which is 3. And then for cell 1, we're going to try the 0, which is value 1, which is the 1 here. So that would be one potential solution. Okay, so yeah, so we've already implemented the basic solver recursion algorithm, but what we're going to do now is, and by now I mean another time because I'm very tired. I'm going to quit soon. Basically what the next step is, we're basically doing the conflict checking, you know, and removing, well, maybe we can do this now. So to remove the related cells, let's have a function that does that. Get rid of that. So let's say const set val IDX val. Let's do it like that, right? And that's basically going to set on the cell with index the value whatever, right? Val. So here we're going to do set val IDX I plus 1. And then that try actually becomes a set val. And we can get a bit fancy here. Like that. And then we're basically going to do this. And we're going to change this to I. So there's no conflict anymore. If I equals val minus 1, val 0. Right, and then post set val, we can do options dot slice IDX times 9 to IDX times 10. And then we don't have to do this anymore. Oop. And now the set val can do the cleanup, the affected cells, right? So we go here. So we are setting cell index 0 to value 3. And slice, options dot slice. Is that not the right syntax? Index times 9, index times index. I thought it was going to be smart, but for index 0, that obviously doesn't work. So, and we can join that. Is there something about smell of cooking rice that I really like? It smells so nice. So we're setting value, and it's now a 3. This is now the 1, and this is now, okay. And we can do that. Obviously, boom. And then we can do ups, and we'll do something like S. And that's our set val here. And we can actually combine these into a retro thingy, retro log. Especially if we type our variables the way that we put them in there. And now tells us exactly what we're doing, right? So we're changing from this to this, from this to this, from this to this. Boom, solution. All cells processed. Now we're returning. Now we're changing. So we're backing up by 1 because the last one only had one possibility. Boom, and it's trying the 2, etc., etc. Right. So the next step now is to update the dependent cells. And currently, do we have a way of doing that? So where are we updating them? Update cell. Update cell. Update cell. So it's updating a particular cell. But in our case, we want to not update yeah, we don't want to do it this way. We want to specifically remove an option. Right, so we have set val. So we want to have a rem val. We want to remove an option. And that basically just means options IDX plus val equals 0. So that's basically all we're doing. So now we can go through the affected cells. Here we go. So set val and affected. And I want to do that now. Affected. Now the problem is the affected cells here aren't indexes. Do we care? Yeah, affected cells, we don't care about the external stuff. So the affected cells, we actually want them as the numerical indexes. So we can filter them and then we can map them to cells.index of cell. So now our affected cells will actually be... Yep. Will actually be indexes, right? So we're setting this to this, and this is affecting 1 and 2, yada yada, right? So now, when we're setting, here, we want to remove from all the affected. Rem val, affected IDX I, and the value being val. Right? And probably want to do the same thing we did here, actually. Just for illustration purposes. So that should show us that when we're setting a value, we're also removing that value. So that we're setting this to a 3, which means we're removing a 4 from here. Of course it does. -1. So, setting this to a 3 removes the 3 from here, and removes the 3 from there, but then make a difference, right? So now that should converge us more quickly. Now, obviously, we have a super spammy output now. Let's see how that works. And I feel that it's quicker. Hey, that's actually not that many iterations, right? Now, what we don't get yet is... Ah, yeah, you see, so now it shouldn't be able to make invalid configurations, right? It won't be able... This is a 4, this will... You see, because this is a 4, this actually skips the 4. So the center cell can never be a 4 if this is a 4. And initially, when this was a 3, the center cell went, 1, 4, 5. Why didn't it go to 2? Why did it not try 2? Oh, because it can't be a 2, right? Okay. Not sure why options here show the 2 as an option for the central cell. Huh. You know what? Let's move things in the place. So we have all the functions here. This should be down there. And this should be down there as well. Ah, exactly. So it should actually have that removal already included, right? So here, no, it doesn't have it included. This should not be able to be a 2 because we have a 2 over here. But we're also just calling update cell right now, which isn't really correct. Update cells seen for each. Update cell. So we should be able to just do a remval idx fixed. Right. Remval 0, 8. Okay. 0, 2, 0, 1. 1, 8. Ah, it removes the 8. And it removes the 2. Ah, here we go. Isn't this kind of the same as that? No, it's not, because it's not doing the right maths here. All right. So now we're starting, yeah. So now the 2 and the 8 and the 7 is gone. Okay, perfect. So that's working now. Now, this, why does this skip the 3? We were going from 1 to 4 directly. Ah, sorry. Why is it skipping the 2? Yeah, because there's no 2, right? It's skipping the 3 because it can't be a 3. 4, 5, 6, 9. It's skipping 7 and 8. So now we have much fewer options here, right? And what we can do now is we're going to get rid of the aggressive language here. Like that. Okay. So now these are options. Now, what we really want to do is add them up. Is that actually all we need right now? Are these all the possibilities for these 3 cells? Taking nothing else into consideration. I think that is true. So now all we need to do is having the one problem it does right now, it does not correctly, or it gives me a min and max, but it doesn't let me separate the known from the unknown, which the previous system let me know, okay, the fixed, but I could do this by excluding the fixed cells first, right? So the fixed cells, add them up, exclude them from the list, don't even bother looking at them, right? Because they don't really affect anything. But for now, let's just do this. So minimum infinity. I think that should work, right? And then we can do a sum, right? Const solve sum. And it's basically just got to loop through all the cells and all the options and add them up. In fact, we can just go to just assuming it's a solution, right? Beep, 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 beep. And just add them all up. Sum. If options is a 0, if options is a 1, yeah, we can just sum them all up. As long as there's only one per thing, that's the value, right? I think that should do it. So if we do this, so this is, 3 plus 1 plus 2, 3 plus 4 plus 2 is 9, 3 plus 5 plus 2, and then the largest is 14. Is when there's a 9 in the middle, a 3, there should be a 15. Yeah, exactly. 4 plus 9 plus 2. All right. And then we can just do that sum, and then min equals math dot min sum and max. And then down here, we should be able to min slash max, min max. So on a primitive level, that gives us a minimum maximum for this range, right? So this range currently can be, so let's think it through, right? This could be a 1, this could be a 2, this could be a 3. Minimum 6, yes. Maximum 15. This could be a 9, this could be an, this cannot be an 8, so this could be a 4. And this could be a 2. Now, if we put a 9 at the top, ooh, did that crash it? Wait, I think I might have put a transparent color there. Yeah. Whoop. All right, I'm just gonna refresh. So now we're excluding the 9. Now the maximum value is 12, right? Now this is the correct-ish min-max value. I don't know if that's... We'll have to see now. So if I can take the cage totals into consideration, then this might start making a lot of sense. So for example, if I look at these, and this one, right? So the problem in this case, right, is that it cannot find a valid solution because these 1, 2, 3s eliminate themselves, right? So I guess it would make sense that in a case like this, it just says NA, not available, right? We shouldn't have to expect it to do something impossible. So if this was a 6 instead, right? Let's look at this again. So now, yeah. So minimum and maximum is 19 right now because we have 6 plus 7 plus 1, 2, 3, which is 6. Now if we add this, so it's 23 to 28. How is it at 23 to 28 now? And what was it before 19? Because the minimum this could be is a 4, and the maximum it could be is a 9. So 1, 2, 3 is 6, plus 6 is 12, plus 7 is 19, plus 9 is 28. So maybe this is... I mean, this doesn't take the cages into consideration, except for visibility, which might be enough. It doesn't take the cage summed into consideration. So if we go back to our original test case, which I believe was this. So it's 25 to 42. It ignores the 6, but it takes into consideration how they can be filled, right? So let's actually output the min solution, maximum solution as well. So we have a minimum solution and a maximum solution. So now, if sum equals min, min sol equals options.join, and we'll do the same thing with the max sol. And then we can output min max, min sol, and max sol. So it's kind of a partial solver, really. What was I selecting before? These guys? So the minimum solution is 1 here, 6 here, 4 here. Now that's not a 10, that's an 11. And that's interesting. Why can't we go lower than a 4 here? Well, it couldn't be a 1 if we put a 1 in here. It could be a 2. Why can't it be a 3? Oh, because the 3 ended up in here. So we have a 1, 6, a 4, a 3 here. So this probably could have gone either way. But this couldn't have been a 4, so this had to be the 3, right? Why couldn't this be a 1? Because we already put the 1 in here. So that's interesting, because the 1 could have ended up in here. But I guess the numbers turned out the same, so it didn't actually care. Then we have the 8. Then we have a 1 in the blank down here. And then we have the 2 here. That's the minimum solution. And for the maximum solution, we have an 8 over here. Yeah. So this would be a killer cage sum unaware calculator, which is probably less. So I think this is a solid foundation. And then having the killer awareness, basically any cells that are part of a killer cage that are fully enclosed, cannot exceed that killer cage. So we basically need to have a way of skipping those quote-unquote invalid solutions. The problem is if we end up with no solutions at all under those circumstances, well, we're back in an NA situation, which isn't too bad, actually. So I think to tidy this up, if I can make this actually output this for now, in some sort of cohesive fashion. Holy crap. All right. Don't need any of that. Merge cell group. Whatever are we even trying to output here? My god, this function is a monster. Calc cell range. Cell range. Fixed min max has blanks. So what we could do is we could output the min and max for now. Hey. I just want to, conclude it at something rather than at nothing. That makes sense. Min-max has blank 3. So it's actually still running the original algorithm down here. So return min-max. So if I do this, and then just change it to ignore the fixed part. Min is not defined. Turn min max. Max. do this. So minimum, maximum. So if I change this terminology right now to something like this. And basically just do this, right? And what do we get? Sum 25 to 42. Now, it's a wide range, but it's an accurate range. So if it's something more reasonable, like these three, 21 to 22. Oh, excuse me. So maybe this is a better, more solid foundation. And now we basically just have to implement the cage totals. And the ranges stay relatively reasonable. So I think, even with the logging, I can leave this in and deploy this to beta. I think that's what I'm going to do, to alpha. And I'm going to let ranks know. And I'm going to conclude this. Actually, is there a daily we can play? I need a little palette cleanser. Because this has been a bit of a brain breaker, and I've been redoing the same thing so many times that, oh man, frustrating, I tell you. All right, let's do a daily, and let's do it on beta, so we can test what's currently going on. Move this to the bottom. Let's see how I can get this onto screen. Oh, and we have a timeout. That is not good. Why? There's something going on. It takes forever, and it should not. It's really not complex. I need to do some work on cleaning things up to make it load faster. Like, why is it taking so long? What is it doing? What's happening? I think part of it is that stupid cookie thing where it goes to a third-party site before it lets me load things, and that's this huge time interval. And I wish I could just do away with it. That's taking so long. It's weird. And the fonts, I need to bring them in from the same server and stuff like that. Like, this makes sense. Anyway, let's play this one. What we got? No Sudoku apply. Cells separated by black dot have a ratio of 1 to 3. Cells separated by white dot have a difference of 5, and all dots are necessarily given. No negative constraints. Right. Okay. So 8 difference 5 3. All right. 2 difference 5 7. Okay. Ratio of 1 to 3. 5 6. Let's do all these first. They're easy. All right. Ratio of 1 to 3. Not too like infinite number of options. I mean. 1 1 4 wait, ratio of 3. Yeah, 1 3 9. Especially, yeah, so this has got to be 1 3 9, right? Because there's only one set of cells that fits into a 1 times 3 times, like there's only one cell that can be divided by 3 and multiplied by 3, right? And then 5 from 1 is 6 and 5 from 9 is 4. So these are 4 6 and 5 from 3 is 8. And then these two are 2, 5, 7, 8. 2, 5, 7, 8. And no 7 here. Okay, and then these three are 2, 4, 7, I believe. Okay. 8s, 7s, 5, 6s. All right, so these, so 2 times 3 is 6, 3 times 3 is 9. So these can only be 1, 2, 3, 6, and 9. And then this can't be a 1. This can't be a 9. If this can't be a 1 or a 9, this can't be a 3. And this can't be a 6. That can't be a 2. Can't be a 1 or a 9. Can't be a 3. Neither of these can be 6, so neither of them can be 2s. So therefore, that's a 3. And then 3 can be multiplied by... Okay, and then that's a 6, and that's a 2. All right, that's not a 2. And then that's a 1 or a 9, with a 1 or a 9 down here. 5 difference. It's not that many options, especially with the 2 and a 3 gone. So this can be a 1, 6, 2, 3, or a 4, 9. All right. And then here we have the same options. 1, 2, 3, 6, 9. Wow, this can only be a 6. Is there any other digit? So 4 times 3, yeah, 5, yeah, no, they're all 2. And divide by 3 is only 6 and 9. 9 divided by 3 is 3. So that's a 1 or 2, and that means this is a 3 or a 6, and it's not a 3. No 2's here, so that goes a 2 here. No 9 here. So 8. No, it can't be 8, 3. It's got to be 1, 6 in here. All right. 5. This was supposed to be a 4, right? Okay, but I think we're fine otherwise. So 1, 6 can't be 1, 6. 2, 7 can't be 2, 7. Can't be 3, 8. 4, 9. It's the only option. All right. And then these are 1, 2. So that's the 2. And 5. 1, 5. All right. And then these 3 are 4, 5, 8. Without the 8 there. That's not a 2. So that's a 2. Oh, and here the same. So we have 1, 6. It can't be 1, 6. 2, 3, 4, 9. And it can't be a 5. So it's got to be this, and that's a 1. So that resolves these guys. 1 plus 4 is 6. 9 minus 4 is 4. 7, 4. And these 3 are 5, 7, 8. Right? And that's a 4, 9. Uh-oh. No. It's a 9, 4. That's a 1, 6. And that's not a 4. 5, 1. 8. 1, 8. Not a 5. Alright. Well, I like the pencil marking. Works for me. 2, 3, 4, 5, 6, 7. 2, 7, 3. Alright. 8 and 7. And then I'm just gonna fully mark these and then just go by the, yeah, that's kind of the sticky point, right? But in this case, I mean, it's just labor. 3, 7, 8. 3, 7, 8. 5, 2, and 7. And then these 2 are 1, 2, 4, 5. 5 down here, 4 and 2. And that resolves these guys. And these 4 is 1, 4, 5, 6, 7, 8, 9. I mean, there are situations now where, I mean, it's really just giving you the easy stuff. It's giving you the naked singles and things like that. So I mean, you can hardly consider it cheating to get those for free, because it's just tedious, right? And there's just potential for errors, and it's not really what you're in it for. You know, that's not what we're here for the puzzles. So yeah. 1. And these 3 are 2, 5, and 6. 6, 5, and 2. And then these are 1, 2, 3, 4, 5, 6, 7, 8, 9. That's an 8. That's a 3. And that's a 4 and 9. Oh, that's a 4. That's an 8. That's a 9. And then these are 4, 5, 6, 7. Not 6. 7, 5, 5, and 7, 8. And that's it. 6 minutes 49. I wonder if certain times are going to get shorter now because of these little tools. But yeah, it's all for the fun, right? All right, that's it. Am I happy with the progress? I feel like this is finally the tool at the level that Ransk was expecting, and he was right. Like, it didn't feel correct what it was doing before. I mean, it's a basic partial solver. No big deal. It'll only work for values 1 through 9, but as long as it just outputs NA correctly, and as long as you're inside a cage, we're falling back to the killer cage calculator. So now the one thing I'd like to add is that once you're including a cage, yeah, for example, if I was solving these, it should just say 16, right? Except the 8 is incorrect, right? This should say 16, that's it. It shouldn't say 15 through 34. That's kind of one last thing I want to do. But then other than that, I think it makes more sense now. So yeah, I think I'm going to record a little GIF after this and send that over. And then that's it for today. Thank you very much for stopping by. Thanks for hanging out. It always helps me. Thanks for your support. Some of the stuff is very tricky, and sometimes I do a bunch of work and then it doesn't make it into the app because I realize I can't do it at the level of quality that I want or the user friendliness. So it's technically possible. There's a lot of unused features under the bonnet for those, like the solver. There's a whole solver in there, but I'm not using it because it's not useful for the kind of users that I think I mostly have for this app. Same with the editor. Like, I've made a lot of progress with the editor, but it's nowhere near yet as easy to use and as comprehensive as I want it to be. So it's going to take a lot more work. So in the meantime, I appreciate your support. I know that people buying SudokuPad right now get an older version of the core engine, and that's really bad. So I'm gonna prioritize updating that in the next couple of weeks. Yeah. In the meantime, patreon.com/SvenCodes. Always appreciate any support you can give there. And even things like helping with testing and finding weird edge cases, all of that stuff helps. Engage on Discord or Twitter. Send me an email. Any help, any kind of opinions, what suggestions, all that stuff. I always appreciate it. Thank you very much for hanging out. Take care. Have a good rest.